Hi there. Today we're going to look at section 2.9. This is the last section that's going to be on exam 2. So exam 2 will cover 2.3 through 2.9. And it's a pretty short section, so let's get right into it. So I'm going to start on slide 2 here and just show you the general idea. It's nice to have a picture when you kind of see this stuff. So the idea is that we want to approximate the blue curved function f of x using a tangent line. And so the idea is, as long as we're close to the point a f of a, this tangent line should be a good approximation. And you can see it from the graph, right? So what we're going to do to approximate a function with the tangent line is called a linear approximation. So when we do a linear approximation, you're sort of plugging in values of x and looking at how accurate the estimates are if we use the tangent line. The function itself, so the actual equation of the tangent line, is called the linearization. So it's really two very similar concepts, but they both use the same formula. And note that this formula is just point-slope form of the line. Right? So here's your y-coordinate, slope, variable, and x-coordinate. So it's exactly point-slope form. So let's jump right in on example 1 and see how this works. So let's find the linearization of f of x equals x cubed at a equals 2 and use it to approximate the number 1.999 cubed. So why do we do stuff like this? Well, the idea is that in the real world, there might be really complicated functions. Maybe you have to program a computer to do something like this. It'd be much easier for a computer to compute a linear function than some complicated function. So that's the idea. So we're just going to use the formula directly. First thing we have to do is write down everything we know. So in order to use the formula, we need f prime of a, and f of a. So there's the function, there's a, and f of a is, of course, 8. So the tangent line is going to pass through the point 2, 8. So take the derivative to get the slope of the tangent line. So there's f prime of x. Compute f prime of a, which gives you 12. So now we know the slope of the tangent line and 2 points on the line. So we use the linearization function, plug in everything we know. So we know f of a is 8, f prime of a is 12, a is 2. X is a variable, so we just leave it x. And our linearization then becomes 12x minus 16. So the line, so the tangent line, 12x minus 16, is a good approximation of f of x equals x cubed at the point 2, 8. So if we want to compute the linearization of 1.999, instead of computing 1.999 cubed, we plug it into L of x, which is an easier calculation. And we get 7.988. So is that a good approximation? Well, in order to check whether it's a good approximation, you can look at the graph. So 1.999 is really close to 2. So it looks like it's going to be really, really close, right? And the reason that we use linear approximations is that we're able to plug in lots and lots of values. If we want to estimate lots and lots of values, it's much easier to just use an approximation, especially if you're just trying to estimate something. So I went ahead and did all the calculations, and I looked at 6 different points on the function and the equivalent points on the linear approximation to see if the linear approximation is a good estimate. So the one we just did was 1.999. The actual value is 7.98801. The estimated value is 7.988, which is an error of 0.00001. So it's accurate to 4 decimal places and very close to 5 decimal places. And then you can compute the relative error, where you divide the absolute error by the value of the function. So we're mostly interested in the relative error. You might call it the percent error, right? We could convert this to a percentage if we wanted to. And what you can see from the table is that the numbers that are very close to 2 have a small relative error. If you move out a little bit, 1.99, 2.01, the relative error increases a little bit. And then if you move away even more, so 1.9 and 2.1, the relative error really starts to increase, right? And that makes sense, right? If you go back and look at the graph, as we move away, the difference becomes bigger and bigger and bigger. And relative to the value of the function itself, its percent error becomes bigger. So this is just a good overview of what we can use this for. So as long as, let's say you need to have an estimate accurate to 2 decimal places, or a relative error accurate to 3 decimal places, these 4 middle values would be fine, but the 2 on the ends just aren't good enough. That's sort of how it works. So this is used a lot in manufacturing technology as well, and data science, and basically everything in science uses this. All right, so that first example is what you're going to see for like the first part of your homework. It's really just tangent line, plug the numbers in, and compute the difference, or the relative difference. Now we're going to move on and look at something a little bit different, still uses tangent lines. It's called a differential. So the differential is just a variation on the derivative formula, right? Remember, the formula for a derivative is dy over dx equals f prime of x. So instead of considering that a derivative, what if we consider dy and dx to be values, to be numbers, instead of just placeholders for taking a derivative? So that's what we're going to do, right? So we're going to take dx to be just a small amount in the x direction, multiply by the slope of the tangent line, and you get a small amount in the y direction. And that's shown here on this graph. This graph shows you everything. So here's x plus delta x. So delta x is the actual difference in the x direction. Dx is what we're calling the estimated value. These now, in the x direction, they're the same, because these are measured values. However, the y coordinates are computed values. So here, when we move from P and then move across the function, we go from x to x plus delta x. The function goes from whatever this y coordinate is up to whatever this y coordinate is, and that difference is delta x. Oh, sorry, delta y. This difference here is delta y. So the function, when you go across delta x, you go up delta y. If we're using the tangent line to approximate the function, when we go over dx, we go up dy. And that can be shown here in this graph. This is dy, and this is just f prime times dx. So the slope of the tangent line times the distance in the x direction gives us a distance in the y direction. Right? It's just a slope. That's how slopes work, right? It's rise over run. That's basically what we're doing here. All right, let's see how to use differentials to just compare some numbers. So here is our function. F of x is x cubed plus x squared minus 2x plus 1. And we want to look at two different things: when x changes from 2 to 2.05, and when it changes from 2 to 2.01. So we already know what to expect. We expect that from 2 to 2.05 might be a good estimate, but it might be off a little bit. But we would expect from 2 to 2.01, we would expect that estimate to be a lot better. Okay? So let's see how it goes. So first thing we want to do is we need to find f prime of a. So in this case, a is 2, right? It's given in the problem. We're going from 2 to 2.05. So x, that's our starting point. right? So we just want to find f prime of 2. So first thing we do is take a derivative, obviously. You guys know how to do derivatives, so I'm not going to spend any time on that. Then we compute f prime of 2, and we get 14. So when we use our differential formula, we're going to plug in 14 every time we see f prime of 2. So for the first part, we need f of 2. That's 9. So the y-coordinate at 2 is 9. The y-coordinate, the actual y-coordinate, at 2.05, plug everything in, you get 9.717625. So the delta y, the actual difference in the y-coordinates, is just the difference of those two y-coordinates, and you get 0.717625. So that's how much the function actually changed from 2 to 2.05. Now we want to find dy. So we use our differential formula, right? dy is f prime of x dx. So f prime of x is f prime of 2. We already find f prime of 2. It's 14. And then dx we actually have to compute, right? dx is the difference in the y-coordinates. I'm sorry, the difference in the x-coordinates. We plug in 2.05 and 2. So it's just 14 times 0.05, so we get 0.7. So if you look at these two numbers, you can see that they're pretty close, but they're really only accurate to 1 decimal place. So if you only need 1 decimal place accuracy, this would be fine. So let's do this again, but this time go from 2 to 2.01 for part B, and let's see if we get a more accurate estimate. So we already know f of 2, so we compute f of 2.01, get 9.140701. Then delta y for this problem is just f of 2.01 minus f of 2. So subtract and you get 0.140701. And then do the same thing with dy, same thing we did in part A. Just plug in new values, right? So f prime of 2 is still f prime of 2. But our dx is different now, right? Our dx is 2.01 minus 2. So it's 14 times 0.01, which is 0.14. So you can see here, this one is much more accurate. This estimate is accurate to 3 decimal places. This was accurate to 1. This is accurate to 3. That sort of makes sense because in part B, you're not moving as far down the function. So the tangent line stays closer, and it's a better estimate. And that's how it works. So in the next example, we're going to see an application of this, how to use differentials to solve problems. So this is going to look a lot like a related rates problem. It's not that similar to related rates. So let's jump right in. The circumference of a sphere was measured and found to be 74 centimeters with a possible error in measurement of at most 0.5 centimeters. So the circumference of the sphere, 74 centimeters. So that means it's a sphere about this big. So maybe it's a bowling ball or something. And the possible error in the measurement is at most 0.5 centimeters. So the error in the circumference measurement is a little half a centimeter. Does that seem like a big error in measurement? That's what we're going to discover. We're going to see, does that small error in measurement affect the volume of the sphere significantly, or would it affect the surface area of the sphere significantly? We don't know. We're going to find out. Because it's not a very big error in measurement, right? It's like not even a 1% error in measurement. But let's see what happens when we apply that to the volume or the surface area. All right, so for part A, we want to do maximum error and maximum relative error, and using this value of the radius to compute the volume of the sphere. And in part B, we're going to do the same thing, but with surface area. So before we get into number crunching, I just want to set some things up. Just write down everything you know. Circumference, got it. Error in measurement. So we're going to treat that as like, with our differential, as like our dx. Remember, you plug in a known value, multiply it by the derivative, and you get a estimated value for the change in y. So this has to be our what we were calling dx. I'm going to give it a new name because we're going to use different variables. But this is what we were calling dx in the previous example. So we have a circumference and then a small error in circumference. But it's asking us to use the radius to compute the volume of the sphere. So the first thing we have to do, write down what we're given. So I'm calling C 74 centimeters. I'm calling that the circumference. DC, that's the small error in circumference, 0.5 centimeters. So I could call them X or Y, but just name the things something that you can remember what it means. Now we're looking for, in part A, we're looking for dV. We're looking for how much does the volume change with a small measurement error in the circumference. And for part B, we're going to look for how much does the surface area change. So we're going to do some preliminary calculations first. I'm just getting all these calculations out of the way early. That way I don't have to do side work. I'm doing all the side work early. First thing, need the circumference formula. Because we need to find the radius. We need to plug the radius in to compute volume and surface area. So I need to solve this for the radius. Now, I know the circumference and I know the radius, right? So plug in C equals 74 centimeters, and we get 37 over pi centimeters for the radius. I'm just going to leave it like that. I don't want to have a bunch of decimals in these calculations all over the place. I think it's a lot easier to leave everything in a nice, I mean, it might look ugly, but hopefully the pi will cancel or something like that, so we don't have to mess with it. Now I'm going to compute the differential. I know I'm going to need a differential because there's a dV and a ds up here. And those are going to be, I either have to multiply those by dc or multiply them by dr. I want to do everything in radius. So all I do is I compute the differential of this. I just take the derivative of this on both sides, right? So r becomes dr, c becomes dc, and constants stay constants. Okay? Remember, this is not related rates. There's no chain rule or anything like that here. I'm just taking the derivative of both sides sort of with respect to themselves, right? It's a ratio. Now, I know dc is 0.5, so I'm just going to plug it in and get dr. So now I have everything I need, okay? I needed r to do the volume calculation and the surface area calculation. I needed dr to do the differential calculation for the volume and the differential calculation here. So this will help me find the volume. This will help me find dV. This will help me find surface area. This will help me find ds. All right, so those values we're going to take as being known values because I already computed them. Let's move in and do part A. So the differential formula is just going to be, and if you're not sure how to build this thing, just think, what is v prime of r? Well, that would be dv dr, dv over dr, multiply both sides by dr, because we're treating it as a number now, and you get dv is just v prime of r dr. If this stuff is still a little fuzzy, just go back and look at the picture from the previous example, and that's what we're doing, right? All right, so the volume of a sphere is 4 pi r cubed. So we're going to plug in our value of the radius computed on the previous slide. I just crunch all those numbers all the way across, and I left everything in this form. I could have rounded it and done decimals, but just, it's best to keep exact values if you're not sure. So I'm going to hold on to that number because I'm going to need it. Next up, v prime of r. That's just the derivative of this with respect to r. So we know how to do the power rule. Again, no chain rule, because it's not related rates. Then I plug in v prime of my known radius. And I just crunch all the numbers all the way across. And I get 54/76 over pi. So I know the volume of the sphere. And I know the rate of change of the volume of the sphere relative to the change in radius. Right, that's the v prime of r. Now I set up my differential equation here. And then I just plug in everything I know. So I know v prime of r. That's 5476 over pi. I know dr, found it on the previous slide with the preliminary calculation. That goes here. Crunch everything all the way across. Now for a final answer, go ahead and round it. You have a problem like this on the homework. You basically want to avoid a lot of early rounding because you got to follow the rounding instructions for the homework. So the change in volume is up to 139 cubic centimeters. So think about it. That's actually a pretty big amount, right? So just having a small error in the measurement of, I don't know, something roughly bowling ball sized, small error in the circumference measurement really can affect the volume measurement. Now, what about as a percentage? Well, the relative error in volume is just dV divided by V. Again, I don't want to put any rounded numbers in here, so I went back and plugged in the exact values here, right? So for dV, I plugged in this exact value. This is rounded. And for V, I plugged in this exact value. Turns out those pi's canceled, like I was hoping they would, and you end up with 0.02. So there's a 2% error. So a less than 1% error in circumference can result in up to a 2% error in volume. So if you're making a bowling ball, 2% difference in volume could be, you know, up to maybe, I don't know, a quarter of a pound in weight, right? You'd notice that if you're a bowler. So you can see how this applies to manufacturing technology and anything else where measurements are made and estimates are done, but nothing's really perfect, right? Okay, let's do the surface area one. So same sort of thing, right? Just build your equation with your differentials here. So the formula for surface area is 4 pi r squared. Yes, it's not a coincidence. That is the derivative of the volume. That's just the formula. There's a good video on 3 blue, 1 brown, why that's true, for those of you who really like math and want to check that out. So we're finding the surface area. There, remember, our radius is 37 over pi. Plug everything in. Right, there's your surface area. Yes, it's the same as the volume, except it's centimeters squared, because we're talking about an area, not centimeters cubed. Then we compute the differential. So we take the derivative, plug everything in. We get exactly 296, because the pi's cancel. Then our ds is just this formula here. S prime of r is 296. dr, we computed 2 slides ago in the preliminary calculations. You get 74 over pi, which is just 24 square centimeters. And so the relative error is just ds over s. Ends up being about 1.4%. And there you go. That's how you do it. So you have a problem just like this on the homework. Make sure you can do this one. This is, I mean, problems in this section all look really different, but this is a good example of sort of an application problem where you have to be really organized or you're going to get mixed up. And now, the way I showed you to solve it is not the only way to solve it. There are many, many ways. You would do well to take my advice and solve it the way I solve it. Because if you make a mistake, when you're super organized like this, you can go back and find that mistake. All right, well, that's it. If you need extra practice, lots of good stuff in section 2.9. And, you know, you can check out the free resources. Again, lots of good videos here. And if you guys have questions, email me or post on the discussion forum. This is the end of the chapter of the Unit 2 exam material and the end of Chapter 2. And so I will be posting review material very shortly. So by the time you watch this video, there will be some review material posted for the exam. So that's it for today. I'll see you guys next video. And until then, study hard. See ya.